Cool. Okay. So this is a quick kind of presentation um of my final project for ENPM818J or real-time operating system. So I implemented a real-time position I guess let's just change that. Position control. Real-time position control of a brushless DC motor. Yeah. So, the team, it was just me. I'm an aerospace engineering master's student. I like space robots, I like human spaceflight, and I like human and robot collaboration in space, if you could guess. Cool. So the mission statement for this project is we wanted to control the position of a hobby grade brushless DC motor. Uh, I think the hoverboard motor can count as hobby grade because it's not super fancy, but it's a beefy thing. So we wanted to control the position of it. So some of our mission level requirements were we need a fast control loop to implement the PD controller. We needed to track the position of the motor, so we have an encoder. We needed to use a brushless DC motor and also a brushless DC motor driver. And here are the some of the reasonings for these requirements are a PD controller or even a PID controller needs to run at a relatively fast rate for good tracking of the motor system. Um, You also need a position sensor to read where the position of the motor is, or else you wouldn't really be able to command it. I mean, you could, but if you wanted to use a PID controller, you need that input at the very least. You need a physical actuator to drive the system. So if we wanted to make an actual servo, we need to actually have a motor. And that's what the brushless DC motor is for. And they're also more challenging to work with than a brushed DC motor, which is why I wanted to use a brushless one because it was more challenging of a project. And then we also needed a motor driver to convert the command signals to phase current cycles. Basically, we needed a way to convert voltages or like digital commands to actual current. And while developing one was originally the idea for this project, it was kind of out of scope, so we left it out. We as in, well, it's just me. Well, yeah. Uh, so we have some system level requirements, which are a little lower level than the mission ones. We want a control loop that can run on the order of 1 kilohertz. So just a generic control loop to run at that speed. Uh, we wanted the ability to read the encoder pulses at a frequency of around 10 kilohertz, and that's because with initial testing, we saw that just kind of shaking the encoder back and forth, we saw that it could reach up to 10 kilohertz frequency, and our motor isn't supposed to be moving super fast, but we need the ability to generate a pulse width modulated signal because that is what gets sent into the motor driver. We need ability to send out digital outputs fast because we need to command a direction pin. And then we also need to control, we need a circuitry for a control input, so a potentiometer in this case. And the reasonings for these requirements are PID controls needs to run at a high frequency for stable and smooth control, which we kind of touched on in the mission requirements. So it can't just run at 10 hertz or 1 hertz. Even 100 hertz is kind of low for it. I mean, you could get motion out of these, but you have so much error between your two systems that you're going to struggle to get good tracking. A high resolution encoder generates a lot of pulses, faster than what a normal while loop on just the ESP32 or even interrupt services can sometimes handle. So having a dedicated way to read in pulses is good. Uh, we needed a higher frequency PWM signal allows us to control the motor a lot smoother. So we could have done like a 1 kilohertz PWM signal generator, but it just would have been a lot more jittery and maybe not. It may be a lot more louder on the motor side. We need to be able to control direction, which I mentioned, which is what the digital output's for, and it needs to be able to do it as fast as possible. And then at least as fast as the actual control loop. And then we needed a user input to demonstrate the motor control. So here's the final system. You can see there's some 80/20 holding up the system, the power supply, the motor, all that kind of stuff, and the wiring that goes with it. On the very left is the system. On the middle is kind of a close-up of the actual motor and encoder setup. And then on the very right is how the motor is actually mounted. Because this is a hoverboard motor, the whole thing spins. That tire metal casing actually spins rather than only some of it or part of it or the shaft spinning. So while you can spin the shaft, all the wires will spin with it. So we spun the entire system which which had a lot of I think inertia, or the system has a lot of inertia because it's basically a flywheel. Uh, Here's some pictures of the electronics, which are crudely thrown together. Um, the potentiometer circuits on the left, and then the motor driver circuit is on the right. So some of the core components was this motor driver, which is a three-phase brushless DC motor driver that takes a PWM input. The hoverboard motor was a core component. I was given a broken hoverboard and I ripped apart the motor, so that's how I got that. 8020 was used to build the structure, and it allowed for kind of a modular system where we could adjust the height of the encoder and the distance of the encoder so that we can actually get ru relatively stable connection, because none of it's very precise in terms of where the encoder should be mounted. And then, of course, we have the ESP32 and then the quadrature encoder. Um, cool. Some additional components were the Wago connectors that you saw in a couple slides back. Um, Down here is some. So these were really useful for connecting wires together. Um, Pretty much that's all I mean, they're probably useful for a lot of other things, but really I use them to connect wires together. The breadboard was used for the digital signals. We had a 30 volt, 10 amp power supply, which is driving the entire system. Um, an enable and disable switch, so it's a physical switch that I can turn on and off, and that allows me to either enable the motor or disable the motor. A potentiometer to command the motor to a certain position, and then a C clamp actually holds the motor in place. So kind of rough setup. So our PWM frequency we set at 20 kilohertz, which computed to a max duty cycle of 248 bits. So that means we can send 0 up to 248, and 248 represents our highest frequency. And we had a resolution of 1 bit, so we could do 0 or 1 or 2 or 3, and the outputted PWM signal should reflect that. Our PID control loop, we got to 1 kilohertz, so that was nice. I had some trouble going from 100 hertz to 1000 hertz. I didn't realize it was a setting I had to change, but I did change the setting and it started running at 100 or 1000 hertz, so that was nice. Our PD controller gains, I didn't spend a lot of time tuning, but I did try to tune it as best as I could. It was interesting. I was oversaturating it by having like a KP of 10, so the motor would just be super fast and always be at its max duty cycle. But going to lower gains, lower than 1, actually kind of helped smoothen out the motion. It's still a little jittery though, and I believe that's because of I think both the potentiometer jitter and the velocity, the derivation of the position jitter. So our control input is running at 100 hertz, and our data logging is running at 10 hertz, and I'll get to that in the next slide. So our main control task, we have 3 tasks. Our main control task is on an entirely separate core these priorities are wrong. Um, with a priority of 10, although it shouldn't really change anything because there's no other tasks running on that core. And the other 2 tasks are running on the current slide. The other 2 tasks are running on the first core or the 0th core, and the input control task, so what reads in the potentiometer, is running with a priority of 5, and the data logging loop runs with a priority of 1. So ideally, the potentiometer should take precedent and preempt the data logging because the data logging is only worried about um, logging data. And something I didn't mention actually in the code overview video that's going to be somewhere co-located with this is that the mutex or the mutex semaphores that I'm using to um, lock the shared buffers has a 0 wait time. So if for some reason the input control task wants to write to the command buffer, but the data logging task is using the command buffer, the input control task will not block. It'll just rerun and keep generating control until it gets lock. And I think that's better because it just will keep the command to whatever the last value was until it gets a new updated one. And although that might have a big discontinuity from the previous to the next, I think it's better than having the system block. But yeah. And then, of course, there is an accompanying video of me going over the code, and then the GitHub write-up has a bunch of more information about the system and not just the system requirements. So, yeah, thank you so much. Cool. Okay, this is my code overview. So we're gonna go quickly, kind of through the code. Not like quickly, but we're gonna go look through the code, just to provide a video of going over it. So my file is called the main thingy. I didn't know what to call it, and I kind of liked it when I initially wrote it, so I'm going to keep it that way. We're using a few C libraries. Math is important because we need the absolute value function from it for floats. We're using a bunch of ESP32 libraries, so logging, sleeping, although we don't really sleep. The error catching, the ADC, drivers. We're using the pulse counter, the GPIO, and then also the LED. Whoa, the LED PWM generator. And then we're pretty much just using all the free RTOS libraries that what am I doing? That you might expect. I have Q in here because I used it, or one of the programs used it, but I didn't want to get rid of it just yet, just in case. But we're not really using it. There are some debug setups, so I made a bunch of initial log tags. So like you would have your position control loop would have this preface in their print statement, and then same thing with the main loop and the potentiometer and the display. Although these aren't really display one is used, but these ones aren't really used. They are called once, and I'll show you that, but we don't call it in a loop to save resources. I needed to define pi because pi didn't exist. Um, I stored all my GPIO up here, so or my pins. So these are all the pins I'm using. We're not using the break pin actually, but they have the functionality to break the board, and as in break the motor, as in hold position, but I don't think that's worth implementing. The enable pin also isn't being used. That is being directly controlled by a physical switch, and I think that makes it better. Although this could be used as like a safety feature in the software if you wanted to program it to enable or disable the output. Yeah, this is a bunch of PWM setup that I pretty much got from the LED code. So I'm just mm, yeah, just setting all the channels and the timers, and I'm setting it to high speed mode, and I'm using the APB clock because I want the 80 megahertz clock, because we're generating a 20,000 kilohertz frequency PWM signal. And then we calculate our duty cycle to be 2048, so I just subtracted that's here. But this one's used for computation, so I just subtracted one from it and stored it as a UN16. This potentiometer setup also I got from the potentiometer example, and I don't believe this needs to be an array, but I kept it like this and just made it one element since we're only using one potentiometer to make it as easy as possible. These are more of my setup values. So I have my control loop parameters. Um, I don't believe this is really correct, but we're operating at 28 volts, so I set my maximum control signal to be 28 volts, or 28 outputs. 28 volts as the output converted to PWM. Um, and then I'm going to take the inverse later on for some computation later, and we'll see that in the control loop. But this one's blank right now, just because all I'm going to do is when I need to use it, I'm going to take the inverse of it and store it, so that I don't need to compute that per loop. I set some default count values, so our high count is 24,000 counts, and our low count is negative 24,000 counts. And this just lets us do 10 turns in the positive or the negative direction without overflowing, and that's pretty good for the demo we're doing. And then our encoder is a 600 pulse per rev, and we're doing quadrature encoding using the pulse counter on the ESP32, which means we magnify it by 4 times, which means our encoder counts are 2400. Our control frequency for the position loop is 1,000 hertz or 1 kilohertz. We have this struct defined to store the PID values for whatever controller. I also have this enum to define what PID control we're doing. So we have a standard one which takes the difference in the error, and then we have this velocity one which uses the velocity as the input to the or the uses the velocity as the damping value instead of the difference in or the change in error. These are some gains I tuned. Beta isn't used yet. We wanted to do velocity filtering, but I didn't want to take more time in submitting this. But But these were some gains that seemed pretty good. They didn't. The motor is less jittery with these gains, but it's also kind of slower. So there doesn't seem to be too much of a steady state error. But in the position command, but it definitely isn't as fast as as a higher KP would have. But it seemed to be relatively stable with these, so we're gonna keep it there. These are all for the counter, so just some configuration, and then I default these to be kind of empty to start. They're global because I wanted to have, I mean, they're global because they're used by the PID tasks or the control loop tasks, but I also wanted to be able to switch between two different PID loops, a velocity PID loop and a position PID loop, but I haven't gotten there yet. These are the handles for the task so that eventually we can do switching where we turn a task on. Like there'd be a position control loop task instead of just a control loop task. And then I have some data buffers. So I am storing all of these values um, in each of the tasks, but only printing them in one task. And I'm using a mutex to make sure I don't accidentally access a resource um, when something's being written to. So yeah. This was also pulled from the example, so I won't go into that. Also pulled from the example, won't go into that. This was also pulled from the example, so I don't need to go into that. But for the control loop read, I'm just reading the counter. So I'm just calling the get count function and storing it into encoder counts. Um, yeah, and this is passed in. This wants a pointer, so I'm just passing in the pointer directly rather than dereferencing it. Um, Yeah, my control loop right, I get in the U value and I change it also. So when it exits the function, this is going to be modified. And I clamp it first to the maximum value. Then I use this function or this line of code to generate the signal. So basically, if U is max, then, and I'm dividing by U max. So here I'm getting the inverse. Um, and because this is a global variable, I set it and then I can use it. But if U is at the max value, then this is 1, and that means our output is the maximum duty cycle we could send out. Or the maximum duty cycle we can send out. And if for some reason this is greater than, or our cycle is greater than our maximum duty cycle, then we just clamp it as well. But this should never happen, in theory. Then we also say if we check our direction. So for one direction, we have to set the pin direction to low. So for less, if we're negative, we set the pin direction to low. And then if we're positive, we set this direction pin to high, and that changes the direction the motor spins. And then we update this duty cycle. Next is to close this is our PID loop. So we're just doing a PD loop, which is we're taking the error and multiplying it by K gain, and we're taking the change in error and multiplying it by D gain, and also multiplying it by the frequency. So our velocity loops is a little different where we're taking the error and then also the velocity and we're actually subtracting the two. So this is our main PID task. It's again only doing PD, but eventually incorporate the I gain. So we calculate the inverse here on our first loop. We also get our counts to radians because we want to do all of our math in radians. And then, um, yeah, all of our math in radians because we're not actually commanding encoder counts. We're commanding a duty cycle. Um, so we do all of our math in radians. We set our KP gain or our PID gains. If there wasn't a constant display, you'd see this, and this would tell you kind of your control parameters. We initialize everything to 0, including our control parameter or our control signal, and then we start the main loop. So I don't need that actually. So we read and then we update. This is part of the entire, this is basically the update loop. And then we write. And that's pretty much it. And based on whatever our set enum is, we'll compute either the standard PID or the velocity based one. And then we store our data in the buffers. And then we store our previous data, and then that's it. And then we wait until 1,000, or then we wait until a millisecond has passed. So this code runs faster than 1 millisecond because we're not getting any errors in the control loop. So that's nice. I'll close this up and you'll see we also have the potentiometer functions. I also pulled these from the example, so I'm not going to go into them. And then for the read potentiometer example, I did modify this a little bit, where I'm just reading the last sample and using that as my command. But ideally, I would take all of the samples and maybe take the average of them so I don't get such a noisy value. And then I will. Uh, uh, did I semaphore this? I did. I didn't. I didn't. Oh, let's do that right now. Yeah, cool. Okay. Good catch, Romeo, I guess. But yeah, so then I just get first I convert the value from the potentiometer to a command. So I basically say that once I'm in the middle of the range of motion, that's 0. And if I go to the far end of range of motion, that's negative 180. And if I go to the far end of the other range of motion, that's positive 180. And I use that here. So our maximum value is 4096, I believe. So I just take half of that. Take our data divided by half, minus 1, and then multiply it by pi, and that gives me the output I want. And then I store the actual potentiometer value. And then, yeah, that's pretty much it. Then we break. And then we have our final task, which is our display. And all this does is it just displays our current kind of values to the terminal so that this is separate from these two loops and it can run at a lower priority so that if this is missed for some reason, we're not going to, we want to make sure that this doesn't miss and the PID position task doesn't miss. So yeah, and then I just set everything up in the main function and I create the tasks and I pin them to their cores. So the control loop gets pinned to the first core, and then the other two tasks get pinned to the 0th core, and they run at their set priorities. So yeah, that's the code. We're gonna do a quick build. Oh, that's wrong. So let's open up ESP IDF and let's do build flash and monitor. And while this is going, um, I'm gonna set up a video to play on the side that will show you that while this is running, I'm also getting motor motion. So here, I've started the video, so I'm gonna synchronize it real fast. Three, two, here we go. Three, two, one. Okay, that should be good. So I'm gonna put this camera here. You can see the motor setup after I zoom out. And you should be able to see the display as well, as I am recording. Yeah, cool. Um, yeah, so this is just the data display. And I know it's not like perfectly displaying, but um, I wasn't too pressed with the output. So I'll turn the power supply on, and then I'll turn the motor on, and now I can drive the motor. So yeah, there we go. So this is running in real time, and you'll see that the data changes as I drive this um, back and forth. So I'll drive it to its max, and I'll drive it to its other max, and then yeah, I'll set it back to 0. And I can disable the motor. So I've cut power to the motor, but I am still reading in encoder counts. So you'll see the encoder counts will change and the error will change as I move this. So if I move it all the way and then repower it, now it's um, gone back to its initial position. So yeah. And actually, if I turn the power supply off, um, the potentiometer and the motor power circuit are somewhat isolated from each other. So they're still grounded together by the ESP32, but I can still change the potentiometer and get a reading from it. Right? Yeah, I can still change the potentiometer and get a reading from it, even with the motor power off. So, um, yeah, and also this only works right now because I'm also powering the ESP32 from my laptop. So there is the ability to power it from the power supply itself, but because I just flashed it, that's why. So yeah, That's um that's the setup, and that's the code running, and I'm really proud of it. But I hope it's good. I think I got a lot of the kind of concepts from class into it. I got semaphores and a bunch of tasks that are running and control loop that runs at a certain speed. So I wish I could have gone a little deeper into controlling the scheduling, but that wasn't a feature from what I could tell from art or from FreeRTOS. So yeah, okay, cool. That ends the code overview portion of my submission.